integrating our functions of time. So I've got here a velocity time graph here. Now, what we know is the change of displacement will be the integral from 0 to 4, because when we integrate velocity, we'll get displacement. However, change in distance won't be the straight integral, because we remember from integration in areas, below the axis is actually going to be a negative amount. So that's why it's fine with displacement to just do the whole integral. But when it's distance, we have to think of it like area, where we break it up, what's above, what's below, and then add all those together. And that's what I've done there. So from 0 to 1 it's positive, I'll add that. From 1 to 3 it's negative, so I'll subtract that. And from 3 to 4 it's positive, so I'll add that. So similar thing with the acceleration time graph then. If I wanted to change in velocity, I could do the straight integral, that's not a problem. But if it was changing speed, I'd have to break it up into its areas, work out what's below and what's above. Now if we had to draw our derivative graphs, or in our case we're talking displacement, velocity, acceleration graphs, it's really the same thing, all we're doing is drawing derivative graphs. If I have a stationary point on the function or on the displacement graph, then I know I'll get an x-intercept on the velocity graph, or the first derivative, because stationary points occur when the first derivative is equal to 0. If it's got an inflection point, well, what do we know about inflection points? Well, it'll end up being a stationary point. Why? Because the second derivative will be 0. Possible points of inflection were where the second derivative is equal to 0. So if I have an inflection point, I know the second derivative. Well, if the second derivative ended up being the x-intercept, if I go back a level, it's like I've got in the line above, it must have been a stationary point. If the original function is increasing, then I know the velocity is positive. If it's decreasing, I know the velocity is negative. If the curve is concave up, then I know that the first derivative is increasing. Why? Because the second derivative would be positive. And again, to track back, we know, well, hang on, positive came from increasing, so therefore the first derivative must have been increasing. And if it's concave down, similar idea, well, the second derivative is negative, which must have come from the first derivative being decreasing. So that can help us when we're trying to draw our graphs. What about the type of graph? We might not know the equation, but if we can see it's a horizontal line, we know that when we integrate a horizontal line, we'll get an oblique line, because when you integrate a constant number, you get a constant times x. If you differentiate it, you must end up with the x-axis, because differentiate that constant, you get 0. If it is an oblique line, when we integrate it, we get a parabola. Got to be a quadratic. When we differentiate it, it'll go back to being the horizontal line. If it is a parabola, then when we integrate it, we'll end up with a cubic. And that cubic will inflect at the turning point from what we saw just before. And the oblique line when we differentiate. So alright, things to keep in mind when we're trying to create these graphs. Integration, remember, is area. Integration is area. So on our velocity graph, what we said was the total area will give us the distance, as opposed to the total integral will give us the displacement. So, want to work out distance, we've got to calculate the area. Displacement, we work out the integral. And similarly with the acceleration graph, total area will give us speed, whereas the integral will give us velocity. Okay, let's now look at some questions. We have a velocity time equation here. V is measured in meters per second, and t is obviously then seconds. So what time is this particle at rest? Okay, well, we know it's at rest when the velocity is equal to 0. That's what it's asking us. So I'm solving 2 minus 4 cos t equals 0. Basically, we've just got a trig equation to solve. Yes, all right, I know I'm in quadrants 1 and 4. The acute angle is pi on 3. And we can go through our normal process of solving a trig equation. And I'll answer the question, well, after pi on 3 seconds, then again after 5 pi on 3 seconds. What is the maximum velocity of the particle during this period? Well, they've given me an equation for the velocity. Sure, to work out the maximum, I could differentiate and say, well, that'll occur when its derivative is equal to 0. But it's a cosine function, and I know things about cosine functions. See, I know minus 4 cos t will go between minus 4 and 4, which means 2 minus 4 cos t must go between minus 2 and 6. Well, therefore, the maximum is 6. That's the biggest it could ever be. So if I use my knowledge of the graph, rather than the calculus here, that can give me a quicker solution. There's my maximum velocity. Sketch the graph. All right, we're just drawing a trig graph. Amplitude is 4. We've shifted this one up 2, but it was a negative, so we flipped it upside down as well. The period is 2 pi. I'll mark off my divisions then every pi on 2. So velocity, marked off my divisions. I'll just draw in the axis there, so I've got something to wind it round. There it is at 2. Now, normally we'd start our cosine graph up at the amplitude, but this one has been turned upside down and shifted up 2. So we will end up starting at -2. We're down the bottom here. Then we go to the axis, up, down, draw our curve in, and there's our velocity time graph. It then said calculate the total distance, and I guess that's why it asked us to draw the graph, because we have to consider when is it below and above, because they've asked about distance, not displacement. So between 0 and pi. So between 0 and pi, most of it's above, but we notice here, whatever that point of intersection here is, that's when it's going to change from negative to positive. And that is pi on 3. That would be pi on 3. How did I get that so quick? Is that what we found out in part A? In the first part we found out when that was equal to 0, so we already had that number. So I've got to split it up into 2 integrals, the bit below, the bit above, integrate them, obviously we get the same answer. Substitute in, but you'll notice I saved myself a little bit of time, not much, but a little, because they're both going to go minus when I sub in pi on 3, so I say, oh well, I've just got 2 lots of that when I subtract. Let's say it doesn't save me a lot of time, but save me a little bit of time. And look at this for a wonderful answer, eh? It's 4 root 3 plus 2 pi on 3 metres. That's how far we've travelled. 2004 question, an acceleration time graph. Write down the time at which the velocity of the particle is a maximum. So velocity is a maximum. Well, velocity, remember, is the integral of acceleration. We've got the acceleration graph. So we're saying when is the integral a maximum? Well, integrals are area. I can look at this picture and say, well, okay, I start at 0 and the area is getting bigger and bigger and bigger and bigger. I'm adding more on. Once I hit 2, I'm now going to be subtracting because I've got a negative area. T equals 2 is where it is. That's one way you could do it. Or of course, you could simply now use the calculus and say, well, velocity is a maximum when its derivative is equal to 0. Oh, hang on, acceleration is the derivative of velocity. Oh, look at my graph. When is that equal to 0? It's when t equals 2. There's our answer. At what time is the particle furthest from the origin? And give reasons for our answer. Okay. So what it's asking is, when is its displacement a maximum? When are you the furthest away? So when is the displacement a maximum? I know that displacement is a maximum when its derivative is equal to 0. So the velocity is equal to 0. But velocity is the integral of acceleration. We need to work out when is the integral of acceleration equal to 0. Now we don't have a function. I suppose we could work it out because they're nice neat straight lines. We could come up with an equation and do it that way. That seems like a lot of work though. When is the area above the axis the same as the area below the axis? Because that's when that overall integral will equal 0. The bit above cancel with the bit below. That's essentially what we're trying to work out. And they are nice, neat, symmetric shapes. So, okay, it's going to end up being at t equals 4, just looking at the symmetry of the shape. Okay? Because you've got this rectangle here which is 1 by 3 followed by this triangle, and then we go to a triangle underneath, so we now want the rectangle that's 1 by 3. It'll be when t equals 4. That's when it's furthest away. As I say, there are other ways of doing it. You could work out the equations of the individual pieces of the function, and you could work it out that way. 2007, here's one where you couldn't work out the equation because it's curved. You'd be guessing what the equation is for those bits. But it's a velocity time graph in this case. Using the trapezoidal rule, estimate the distance. And we have to because, as I say, we don't actually have the equation of this curve. So how can we integrate? Well, we can't. but we can using the points that we know. So the trapezoidal rule, h on 2, y n points, so y0, yn, 2 times all the ones in the middle. Well, I've only got 3 points that I know, 0, 0, 2, 1 and 4, 5. So 1 times the endpoints, 2 times the one in the middle, substitute it all in, and there's my estimate. And it is an estimate because we don't actually know the equation of that curve. So 7 metres we're estimating it's travelled in that curvy bit. The object's initially at the origin, during which times is the displacement decreasing. Well, I know it's decreasing when the first derivative is less than 0, or the velocity is less than 0. So I can look at the graph, because I've got a velocity time graph. I want to know, when is that decreasing? Oh, it's decreasing from B to D. So once t is greater than 5 seconds, that's when it's decreasing. Estimate the time at which the object returns to the origin, again justifying your answer. So it's the same sort of question as before. It's saying, well, when's the displacement equal to 0? Right? It's returned back to where it started from. So its overall displacement is 0. Displacement is the integral of velocity, and we have a lovely velocity time graph we can work with. We have to solve that integral. When is the area above the same as the area below? Okay, well, here's our graph. By symmetry, I know the bit from 4 to 6 is going to cancel out. I've got 2 triangles there that are congruent to each other, so the positive one will cancel with the negative one. Now, we estimated that going from 0 to 4, that area is 7. So what we now need to work out is, well, when will this, well, it'll end up being a rectangle. When does this rectangle have an area of 7? So that bit in there, it's going to have some sort of area. I've just called it area 4 because it's the 4th shape. When is that equal to 7? Now I know the height of the rectangle, it's 5. Oh, 5a equals 7. 1.4. But remember, I've got to add it on to the 6, so it's after 7.4 seconds. That's when it will return to the origin. Now we have to draw the travel graph, the displacement time graph. Here's velocity, I'll draw it underneath. Now on my scale here, I've labelled in the same important points here, so I've got 2 and 4 and 6. I've also put in 8, and I've marked in this one here, which would represent where C is, which, because of the symmetry, I'm assuming that's 5, but halfway between 4 and 6. Why did I go up to 9.5? Well, that's because of the information we found out about distance it had travelled and things like that. All right, here's what we know. The object is initially at the origin, so I can plot that point in. I know that's part of the graph. We estimated that when t equals 4, the displacement was 7, so I can plot that point in. Now, we said the symmetry of the triangles, they're going to cancel each other out. So at t equals 6, I must be back at 7 again. Okay, I'll plot that point in. I can actually work out the area of the triangle, and that's why I've gone up to 9.5. The area of that triangle is 2.5. Bang, I'll plot that point in. We also said it returns to the origin at t equals 7.4. So I've marked that point in as well. Here's the tricky bit. If I look at the curve, V is steeper between 2 and 4 than it is between 0 and 2. Well, that means it must have been going faster. Remember, the steeper it is, the faster it's going. Well, if it's going faster, then it covers more area. So when I plot at t equals 2, I'm not going to plot it halfway. I'm going to put it below halfway because it's covered less distance. Well, okay, it's just an estimate. So I'm putting it about there, but it's below 3.5. That's where I've put it. Ah, look at this one. Once we go past 6, we've got a horizontal line. V is a constant. That therefore means when we integrate, we get an oblique line. So we have this straight line going between 0 and 7.4, and it would just keep going just like our horizontal line is going. So I've got one piece of my curve. I know that's going to be a straight line, an oblique line. Okay, there's the rest of the graph. Okay, why? Well, did I put that? Oh, no, come back. See, between B and D, I've got an oblique line. Integrate an oblique line, I get a quadratic. So I know this is going to look like a parabola, that piece here. And here, I know it wasn't linear because it was covering a different amount and so on. So it must be some sort of curve, and I've just drawn a curve in to complete the shape. There's my travel graph, my displacement time graph. Okay, let's try another one. This time we've got a velocity time graph. Shape's a little bit different there, okay. At what time is the displacement, similar sort of question, from the origin a maximum? When is the displacement a maximum? Well, we know displacement is a maximum when the area is most positive. Displacement is the complete integral. When is it most positive? Or another way I can look at it and say, oh, that's when velocity is equal to 0. Problem with this one is, I suppose, it's 0 at 2 points, 2 and 6. Well, which one? Well, I want the one where it's most positive. So that's going to be t equals 2, because after I get past 2, I'm going to have negative values. So it'll get smaller and smaller. So it must have been at t equals 2. When does it return to the origin? You see the same sorts of questions being asked. So when is displacement equal to 0? I'm back to where I started from. Area above, area below. Let's have a look at our area. Going to t equals 1, I've got this lovely rectangle. Its area is 2. I don't know that area there. I'm just going to call it A. But I'm assuming, yes, I'm making some assumptions here, but I'm assuming that's symmetric. Kind of looks like it's got rotational symmetry there. So I'm assuming that that would also be A, and they're going to end up cancelling out. If it doesn't, it's going to make this question incredibly difficult. Add in the rectangle to make it balanced. There's the point that it is back at the origin. Of course, what is that point? Okay. Well, the width of this rectangle here will be W. Well, 2W will equal 2. The width is 1. No surprise there because of the symmetry. Well, the width of this rectangle is 1. So it makes sense that the width of that rectangle is going to be 1 as well. All right, 4 seconds. So after 4 seconds, we're back there. Draw a sketch of the acceleration curve. Okay, there's our velocity curve. We'll put the acceleration one underneath. Again, I've labelled in key points for t here. Let's see what we can do. Well, we've got some horizontal lines. And we know that when we differentiate a horizontal line, we'll get the axis. There's 2 little pieces of our curve I can put in. We just got the axis on those ones. Now, these curves. I don't have the equation, but okay, maybe I'm going out on a limb here, but kind of looks like a cubic. If you imagine the cubic, I'm assuming. I've got to assume something to get this picture. So I'm assuming that's a cubic. It inflects at 2, I know that, and it's decreasing. So when I differentiate, if I'm assuming it's a cubic, I get a parabola. It will be stationary at that inflection point, so when t equals 2, and it's negative, so it'll be below the axis. How far down it goes? Don't know. So, but at least I've got a picture. All right, 5 and 6, what am I going to do? This is where I really had to take a leap of faith. Well, I'm kind of assuming that, hey, that shape's congruent to that shape. I've got nothing else to work from. So I think it's a fair assumption. It looks like it's the same but reflected over. So if that's the case, then I should get, well, it's meant to look the same. I should get the same half of the parabola, but now reflected above. Weird shape, but I think that's what it looks like. So 9C will now play with some of these ideas.